Welcome to section 3.1. We're starting the exponential and log chapter. Please remember, first and foremost, this chapter we start using or taking away the calculators. So what we're going to try and do today is do as much as we can without our calculators so that you kind of get the idea of what we're going to expect you to do on a quiz. So taking a look at this y, either y equals or f of x equals, anything like that. As we look at this, we're looking at this function, y equals 3 to the x power. And I'm going to start by putting exponents in. 3 to the 0 power is always 1 because anything to the 0 power is 1. 3 to the first power is 3. 3 to the second power is 9. And 3 to the third power is 27. Okay, now remember with negative exponents take reciprocals. So 3 to the negative 1 power is the same thing as 1 over 3 to the first power, which is 1/3. 3 to the negative second power is 1 over 3 squared, which is the same thing as 1/9. And 3 to the negative third power is 1 over 3 cubed, which is 1 over 27. And again, you're approximating on your graph as we go through, but let's plot some points. 0, 1, 1, 3, 2, 9. And obviously the 27 we can't put on there, no big deal. Negative 1 is about 1/3, and then a 9th, and then a 27th. And what you'll notice is it gets really close to the x-axis. But I'm going to keep getting numbers that are close to 0, but not actually 0. And so I want to look at the domain, and everything you do should be an interval notation. So the domain, I can put in negative numbers, like -3, -2, -1. I can put in 0, and I can put in positive numbers. So my domain is all reals, or from -infinity to infinity. You'll notice my range. Take a look. I'm getting at really small decimal values here, and then it gets really big quickly. And so what you'll notice, though, is I never have a way of getting 0. So we say from 0 and it gets bigger to infinity, but we can't include the 0 because we won't actually touch it. Do we have any intercepts? Now you want to look at both x and y intercepts. And you'll notice there are no x-intercepts because it's not touching this x-axis. But there is a y-intercept, and the y-intercept occurs, so I'm just going to put y-intercept, and it occurs at the point 0, 1. Are there any asymptotes? Well, yes, we said it wouldn't touch the x-axis, so that's the equation y equals 0. Again, don't write x-axis, we're looking actually for an equation. Is it continuous? Continuous means basically you draw it without picking up your pencil, and the answer is yes. Is the function increasing? Well, yeah, we get from the smaller values up to bigger values, so the answer is yes. Would this pass the vertical line test? Absolutely. The horizontal line test is a little trickier because if you look over here, it looks like it turns horizontal. It doesn't. They keep getting smaller and smaller. If we were to expand this graph on a graphing calculator, you would see you'd never get the same value twice. So it does pass the horizontal line test, which means it's 1-to-1. Okay. Now I also want to talk about when you're graphing, and I'm going to change my color a second, because when you're graphing, I would also like to see you dot in the asymptote. And so that I know that your graph can't touch that. Again, I'm trying to use a whiteboard pen, so it's not as nice. But you'll look and see that your graph can't touch it. Okay? These are descriptions next of transformations. And if you look at the transformations, these really are a lot like last chapter in the quadratic. And so we're going to talk about how it works. If you look here, I'm doing a +2. Instead of parentheses, it's now an exponent. But when the number was tied with the x, it was the opposite. It was like in parentheses. And so this says move left 2. Okay? This +4 at the end is just like the quadratic. If I put a +4 at the end, it means I'm moving up 4. The negative in front of the function means it reflects over the x-axis. And some of you may say, well, how does it reflect over the y-axis? Look at it, it's tied directly with the x and the exponent. So this is a reflection over the y-axis. Now, what you will want to do is plug these into your graphing calculator, but let's just talk about if we didn't, because again, we'll have you do this without. If I graph the original, 3 and 9, let me erase that one, 1/3, you got a 1/3, a 1/9, and it ends up going something like this. So this is our graph 3 to the x, okay? Now if I asked you, and I'm going to go different color each time so you can kind of see. Here's my first one. I'm going to go left 2. So I'm going to take each point and move it left 2. And basically you'll end up seeing this gets really little. This is my left 2 graph. And you'll notice I didn't again use my graphing calculator. Let me change another color. I'm going to do my up 4 in blue. So I take this point here and I'm going to go up 4. Take this point and go up 4. And you can kind of see now what happens. 1/3 go up, 1, 2, 3, 4. And you'll kind of see this graph. Now I want to talk about this up 4 a second because our original asymptote was at the x-axis or y equals 0. If I shift that up 4, then I also have an asymptote now for this new graph at y equals 4. So y equals 4 is now the asymptote for that graph. Okay, let me go a different color again. Let's see if I can find a nice one. Let's go reflect over the x-axis. So I take my red graph, my original graph, and I reflect each point over the x-axis. And you end up getting this graph. You'll notice the asymptote is still at the y equals 0 line. And let's go one more. I'm going to go reflect the y-axis. So this point stays the same, but now I take this point and I reflect it over the y. And I take this point and I reflect it over the y. And I've got now a 1/3 and a 1/9 and a 1/27. And you'll see this ends up reflecting, so it's now decreasing function. But again, the asymptote here is still the same. And so you'll notice if you can graph the basic, and in this case, this would be our parent function. If you can graph the basic parent function, you should be able, without your calculator, to do left, right, up, down. We'll even stretch and shrink and things like that. Okay? The next one, you will need your graphing calculator because we end up putting this, we throw decimals in. And so when you put it in your graphing calculator, one, we have an E, and don't forget that E is approximately the value of 2.71 something, something, something. It's like a pi value. But when you put this in your calculator, you need to make sure you have parentheses around your exponent. So you'll want to stick this in your y equals menu in your calculator, and then go to your table for some values. So obviously anything with E and anything with a decimal will probably have you use your calculator for. And if I go to my table, I end up getting 1.42, 1.82, 2.34, 3, 3.85, 4.95, and 6.35. And so these are kind of the values that you get. One place you want to look is your y-intercept. Again, we have a y-intercept. And this occurs at the point 0.3. And you'll notice that's this value in front. This a value will tell us our y-intercept. So I'm going to start plotting there. 0.3. At -1, again, we're just kind of approximating. 2.3 is here-ish. -2, 1.8, 1.4, and then 3.85, 4.95, and 6.35. Okay, so you'll notice it's curving, it's just curving less. The last one we had curved really quite abruptly. This one doesn't. Again, you can kind of stretch out your window to see how close it gets or where an asymptote might be. But in this case, again, we put in both -0 and positive, so our domain is all reals, which is from -infinity to infinity. The range, again, there is going to be this asymptote at y equals 0. Okay, it's the same thing as the x-axis. We're not moving it up or down any, therefore the asymptote is going to stay at the x-axis. So my range is from 0 to infinity, but don't include the 0 because there's an asymptote there. This again is continuous. You'll notice my graph is increasing. It increases from left to right. It passes the vertical line test. It also passes the horizontal line test, and therefore it's 1 to 1. So again, the points you'll have to get from your calculator. Once you graph your function, though, you should be able to start seeing that a lot of these exponentials really have the same idea, same domain, same range, same asymptote, unless we're shifting it. Unless we go up or down, your asymptote will probably stay the x-axis or the y equals 0 line. Okay, so let's flip the page. One of the things we did in Algebra 2 was the one-to-one property, and basically what it said is if the bases are the same, then the exponents are equal. And we're going to use this idea a little bit more in depth than we did in Algebra 2 to try and make these bases be the same so that we can figure out what x would be since it's in the exponent. When you do this, you always want to use the smaller number. And so the smaller number in this case is 4, so we're going to say 4 to the x plus 1 power. And the question is, can we write 16 with a base of 4? Well, sure. 4 squared is the same thing as 16, so you're picking the smaller number to work with. And now that the bases are the same, I basically can cancel out the bases, and I can say 2 equals x plus 1. And if I solve, therefore, then x equals 1. Now, you'll want to make sure that your algebra is correct. Plug it back in. Is 16 the same thing as 4 to the 1 plus 1 or 4 squared? The answer is yes, so we're good. Okay? I'm going to show you one more because, again, this is going to come up as well. You'll notice now you have a fraction and a whole number. And so I'm going to work with my fraction. Can I write my fraction instead as a whole number to an exponent? And this is 1/3. 1/3 is the same thing as 3 to the negative 1 power. So I'm going to raise that to the x. And now since I picked 3 for this side, can I write 81 with a base of 3? Well, yes, 3 to the 4th power, that is 81. So I multiply the exponents according to my exponent rules. And basically, since the bases are the same, I can cancel them out. So negative x has to equal 4. When I divide by negative 1, then x equals a negative 4. And again, you'd want to double check in your calculator, is 1/3 to the negative 4 power going to get you 81? The answer is yes, so we circle our answer. Okay, we're going to get a bit more in depth with the one-to-one property coming up, but I wanted to give you the idea of it. What I want to do is highlight this radioactive decay formula, because this is one of the formulas you will need. We are not going to give it to you. So I want you to have that as you go through, and let me make this a dark color. The formula for radioactive decay, it's the same thing as a half-life, and the formula then is P equals I, which is your initial amount, times 1/2, and then it's the time t divided by your half-life period. Okay, this is definitely something you need to have memorized. Obviously, half-lives you may, most of the time this would be in the calculator portion, although there is an option for both. So what we're going to do is actually look at an example. Okay, so plutonium has a half-life of 24,100 years. Suppose Marty had 10 pounds of plutonium originally in 1955. How much would be left in 85? All right, well, let's set this up. P equals 10 is my initial amount, and I'm taking a half-life. They basically told me it's a half-life. The time is always in years, so we started in 55, we get to 85, that's 30 years, with a half-life of 24,100 years. So here's the setup. Now the hard part is making our calculators do it what we want it to do. So you'll take 10 times 1/2, and please make sure 30 divided by 24,100 is in parentheses. you end up getting approximately 9.99, and don't forget a label because it does have a story to go along with it, 9.99 pounds. Okay, make sure your calculator can do that as well. The last section we're working on is compound interest. This again is a review from Algebra 2, although we're going to take this a little bit differently as we go through. There are two formulas though that you should know. The first formula is for regular compound interest. It's the fact that A equals P times 1 plus R over N to the NT. And I think this should look familiar to you. And R is the rate as a decimal. Okay, don't forget R has to be as a decimal. N is the number of times compounding. And T is time. Again, time is always in years. And that's kind of important too as we go through. P is the initial amount also. The biggest thing though, when you're talking about N, you're going to see things like daily. Okay, daily is 365. You're going to see monthly. Monthly is 12. You're going to see weekly. Weekly is 52. Let me make sure that looks like a 5. I apologize. What else are you going to see? Quarterly. Okay, every quarterly is 4. Semi-annual is 2. Annual is 1. Not sure if I'm missing anything, but this is kind of the idea. Okay. The second equation we're going to talk about is compounded continuously. I'm going to put that one over here. So compounded continuously, and that equation is A equals PE to the RT. Again, E is that number in our calculator. R is the rate as a decimal, and again, T is time. So I think you've used both of these in Algebra 2. I just want to take a look at a couple of them and kind of make sure. Here's what it says. Mr. Wilcox has $100 in for 1 week of pay. He puts that money into a savings account that earns 6% interest per year. Okay, so what I'm going to do is I'm going to show you kind of a couple of these. What happens if we compound them 1, 2, 4 times a year? We'll talk about a couple general, and then we'll do what happens infinitely. And I'm only going to do a couple of these to kind of give you the idea. You'll want to fill in the rest of the table. So no matter how many times we compound, we always start with $100. Okay, again, the 6% interest is a decimal, 0.06, so that's what we're going to use as we go through. And I'm going to talk about it in terms of N first, and then we'll plug in our N to figure out the one on the left. Basically, if they're multiplying it N times a year, let's look at 3 months. What happens is then I start with my 100, and I do 1 plus, my rate is 0.06, and I'm going to divide it by whatever my N is, to the N times T. Now our time is in terms of years. So we're doing 3 months out of the 12 months in a year. So we're going to raise this to the 3 over 12n. Okay, 3 over 12n. And let me see if I can make this a little nicer. So 3 over 12. So let's say we did it once. What would end up happening then, I'm going to move this equation over here, you'd have 100 times 1 plus 0.06 over 1 to the 1 times 3 over 12. And now you're looking at this going, I don't really need the 1. You're right. What you should end up getting then is $101.47. Okay. Let's look at 9 months, and we'll do it at 4 times a year. As I look again, we're starting with 100. 1 plus, and we're doing it 0.06 divided by n because we're doing it n times. Now again, you're doing 9 out of the 12 months. So we raise this to the 9 over 12 times n. So you're trying to put your months in terms of years. If you did this 4 times, you divide this by 4, and I'd put an extra parentheses, and then take 9/12 times 4, raise your exponent there. You should end up getting $104.57. Okay, and if you're having a problem getting these values, please let me know. Let's do 15 months. So we've done 9 months. Let's do 15 months an infinite amount of times. And if you're doing it infinitely or continuously is what our Algebra 2 book called it, and you'll see both in this book, then we're going to use PERT. And so as I do 15 months, I'm going to say 100 is my original times E to the, my rate is 0.06. And since I'm doing 15 months, I'm going to take 15 divided by 12. Sorry, no, that's a little hard to see. Let me try that again. And raise that. So I'm taking it as 0.06 times 15 over 12. Okay, and again, you need that parentheses around your exponent. You should end up getting then $107.79. Okay, I want you to see if you can fill out your T years later and show me how that formula works. I will be looking for this box to make sure that you have done the notes. But again, take a look. These are again things you did in Algebra 2. We're just kind of redoing them again. I'm going to cross this out. Please look again at your schedule just to make sure if I made any modifications to that. But that's section 3.1. Again, whatever you can without your calculator, you're kind of seeing the first page is more without your calculator. Also, the one-to-one property is without your calculator. The formulas for decay and compound interest will probably be calculator based.